Ansys, Mechanical Heat Transfer. Heating Coil Workshop. Problem description. This model consists of a tungsten coil that is generating heat due to electrical resistance. The load is simulated using internal heat generation. We further assume the coil operates in a vacuum, so the only heat transfer mechanism is radiation. Units setup. Open Workbench and specify the unit system, metric, kg, mm, s, degree C, mod, n, mv. Choose to display values in project units. Model setup. From the Workbench project page toolbox, select a steady-state thermal analysis system. Double-click the engineering data cell. In the engineering data field labeled, click here to add a new material. Enter tungsten. Model setup. From the engineering data toolbox, drag and drop isotropic thermal conductivity onto the tungsten cell. Enter 0.118 W/mm degree C in the isotropic thermal conductivity field. Return to project, right-click the geometry cell and import geometry heating_coil_WS4.x_T. Double-click the model cell to open the mechanical application. Expand the geometry branch and assign the material tungsten to the part. Preprocessing. Change the selection filter to body selection. In the graphics window, RMB select all. RMB insert internal heat generation. Enter a magnitude equals 0.02 W/mm3. Change the selection filter to surface selection. Select one exterior surface, not one of the ends of the coil. Choose to extend to limits. The status bar should indicate 10 faces selected. RMB insert radiation in the radiation details. Enter. Emissivity equals 0.25. Ambient temperature equals 30 degrees C. Solve. Solution. While the solution proceeds, or after it's complete, review the solution information. Change the solution output to a heat convergence. Note, although this was a steady-state solution, the radiation boundary condition makes it nonlinear, as the convergence behavior shows. We will discuss nonlinear solution options in the next video. Post-processing, checking for a steady-state condition. We note, volume equals 15,982 mm3, heat generation equals 0.02 W/mm3, total heat generation equals 319.6 W. Drag and drop the internal heat generation boundary condition onto the solution branch. This creates a reaction probe. Evaluate results. Note the calculated reaction, 325.2 W, is within 2% of the actual heat generation above. Again, the next chapter details conditions and controls that can affect nonlinear accuracy. Results. Add temperature results and evaluate. Scoping to individual surfaces allows more detailed results to be viewed. Heat transfer basics, symbols and conventions. Heat transfer basics. Characteristics of FIA thermal solutions. Boundary conditions. Thermal structural comparisons. Workshop. Following symbols will be used throughout: time, temperature, density, specific heat, film coefficient, Stefan-Boltzmann constant, thermal conductivity, heat flow rate, heat flux. Internal heat generation/volume. Energy. There are three basic modes of heat transfer: conduction, internal energy exchange between one body in perfect contact with another or from one part of a body to another part due to a temperature gradient; convection, energy exchange between a body and a surrounding fluid; radiation, energy transfer from a body or between two bodies by electromagnetic waves. In most cases, we analyze heat conduction problems with some combination of convection, heat flux, specified temperature, and radiation boundary conditions. Conduction heat transfer defined by Fourier's law of conduction, heat flow rate per unit area in direction n. Negative sign indicates that heat flows in the opposite direction of the gradient, i.e., heat flows from hot to cold. Convection heat transfer is defined by Newton's law of cooling, heat flow rate per unit area between surface and fluid. Convection is typically applied as a surface boundary condition. Convection coefficient and bulk temperature are user inputs. Radiation heat transfer derived from the Stefan-Boltzmann law, heat flow rate from surface I to surface J. Radiation in Ansys mechanical is treated as a surface phenomena where bodies are assumed to be opaque. In mechanical, only radiation to ambient is used, Fij assumed to be 1. An advanced section in this course will cover surface-to-surface radiation. First law of thermodynamics, conservation of energy requires that the net change of the energy of a system is always equal to the net transfer of energy across the system boundary as heat and work. Conservation of energy, for a small time increment, can be expressed in equation form. When one applies this to a differential volume, the governing differential equation for heat conduction is obtained. Sources of singularities, poorly posed problems. In a steady-state analysis, when heat is supplied, e.g., applied nodal heat flow, flux, internal heat generation, with no heat flow outlet, prescribed nodal temperatures, convection loads, etc., the steady-state temperature is infinite. Equivalent to rigid body motion in structural analysis. Thermal gradient/flux singularities. As mesh is refined near a point heat source, the gradient/flux is observed to increase without bound. Reentrant corners and cracks in mesh cause difficulties. Poorly shaped elements can create anomalous results. The well-posed problem: when setting up a thermal analysis, there should be an identifiable path for the heat flow. Steady-state problems require both a source of heat and a heat sink. Having no heat sink is analogous to a completely freestanding structure subjected to a load. Transient heating problems do not require heat sinks, but will not have steady-state solutions without one. Proper specification of boundary conditions is crucial. What is realistic? What do you know? Is the heat load known, or a function of an unknown temperature? Overspecification will lead to incorrect solutions. Nonlinear problems benefit from good initial guesses for temperature. Specified temperature: this is a common approximation, and since temperature is the degree of freedom, DOF, Ansys will solve for. Its specification makes the problem easier to solve. The user must verify that this is a reasonable assumption. If a temperature is specified, the physics of the problem must dictate that this temperature is maintained. Therefore, at a specified temperature there will be a heat flux calculated which maintains this temperature. A simulation that contains only specified temperature boundary conditions will always be bounded. If the conductivity is constant, the solution will be independent of conductivity. A temperature applied as a step change during a transient analysis is generally difficult to resolve. Convective boundary, Newton's law of cooling. This condition implies there is a flow condition that serves to carry heat to or from a surface. The effect of the flow on the surface is simulated although there is no actual flow modeling at all. Two items are required: the ambient temperature, the heat transfer coefficient, HTC, or film coefficient. HTC values are commonly obtained from correlations for specific flow and heat transfer conditions. The HTC may be thought of as a proportionality constant between the surface temperature and the ambient temperature. For a convective boundary, both the surface temperature and the heat flux are unknowns which are calculated by the Ansys solver. Heat flux, heat added per unit area per unit time. Applied to a face. If the geometry, area changes, the amount of heat added will change. Heat flow, heat added per unit time. Applied to a face, edge, or vertex. If the geometry changes, the amount of heat added does not. Radiation, the radiation boundary condition employed in mechanical is a far-field condition. That is, the surface in question radiates to a far-field ambient temperature condition. This is a special case of radiation between two surfaces when one is much larger than the other. Surface-to-surface radiation transfer is possible in mechanical only with command objects. This is an advanced topic covered in a later chapter. Adiabatic boundary, if no other conditions are applied to a surface, it is an adiabatic boundary. The heat flux at an adiabatic surface is zero. This is the natural condition when no BC is applied in Ansys mechanical products. The perfectly insulated boundary in mechanical is equivalent to an adiabatic boundary. It is generally only used to overwrite another condition that has been applied. These are some common analogies relating thermal quantities to structural quantities. Structural, displacement force pressure strain stress reaction forces thermal, temperature. Heat flow rate. Heat flux. Thermal gradient. Heat flux. Reaction heat flow.